Welcome to my YouTube video, which is dedicated to the learning of applied mathematics in structural engineering. So today we will continue using Laplace transform to resolve differential equation to find the deflection of the beam, the elastic curve of the beam. So here we have the example of a horizontal beam with length 2L that has a fixed support at point A and simply supported at point B and C. The beam carries a concentrated load P and a uniform load Q per unit length, and we assume it has a constant EI. So today we'll try to find the support reaction MA, and moment at point A, RA, RB, and RC. And we will find the equation of the elastic curve, and then also try to visualize or plot the beam deflection and the moment diagram, assuming P equal L equal EI and the L is all one unity with value 1. Before we can apply the Laplace transform, we will define the load as follows. So the concentrated load we will define with the help of direct delta function, and the uniform load we will define it as with the help of unit step function. And the point B is the reaction, RB is a minus. Here positive sign is pointing downward, and here this will be the reaction B pointed upward, so that will be negative, that as considered as the load. And the governing differential equation is the fourth derivative. Now we need to do a Laplace transform of this equation, left hand and right hand side. Then for the Laplace transform of derivative, we have discussed this in the second video, so I will skip this one. So we use this fourth derivative, Laplace transform of the fourth derivative. Then we have this result after taking the Laplace transform of the equation 1 of the differential equation. So single concentrated load P, uniform load Q, and minus the super reaction at point B. Now we will always have 4 integral constant that come from here, C1, C2, C3, C4. Applying the essential boundary condition at point A, fixed support, where deflection should be 0 and the rotation should be 0, then we can cancel out these 2. Then we end up with only have C1 and C2, where C1 is the second derivative, C2 is the third derivative. Then we will do the inverse to get the elastic curve equation. Now we can drop this unit step function, noting that the value, if x equal a, then this value, this terminology can be dropped. This term can be dropped. So we have a simplified equation. So if x smaller than L, then we can ignore this one. And the same for this part. If x smaller than half L, then this lost its meaning and can be dropped as 0. Now we can apply the essential boundary condition at point B and C. So remember, we have 2 integral constant that we need to find its value, C1 and C2, and we have 2 equation that we get from applying the boundary condition at point B and point C. So we get C1 and we have C2. Now with these 2 equations we get C1 and C2, and you will notice that inside the C integral constant C1 and C2 we have this one unknown variable, support reaction RB. So how do we will solve to get this value RB? Then we apply the last boundary condition that at point C, where x equal to L, the moment should be 0. Then we can resolve this equation to get by substituting C1 and C2 from the previous equation here of applying boundary condition. Then we can resolve that RB is this amount. And then we also know that C1 is the moment, fixed and moment support at point x equals 0 is MA. Then by taking the second derivative of the elastic curve, we can see that MA is equal EI multiplied by C1. Then we can resolve for the fixed and moment support at point A. Then we can continue by finding the vertical support reaction at point A, where x equals 0. It should be the minus of the shear force, or the third derivative of the elastic curve. Then we get the support reaction RA. And finally, to get RC, one of the simple ways is to use a static equilibrium, that the sum of vertical force should be 0. Then we can get that QL plus P minus RA minus RB is equal to RC. Then we have the final result. RA, RB, RC, and the fixed end moment at point A. If you check, you will always find this all in the meet the requirement for the static equilibrium. Then now we can plot the visualization for the elastic curve using this equation. The y as a function of x, and we can plot, assuming P equal Q, EI, L all is one unit. And we see the visualization of the elastic curve for this beam example. And then the moment bending is here. So you see that using this Laplace transform to resolve the differential equation, we have only one differential equation for the whole length of the beam. We don't need to cut the beam into several segments. And in the next video, I will show how to use the so-called singularity function that was introduced by Macaulay, or we can call it Macaulay method, to resolve the differential equation for the beam. So in the next fourth video, we will discuss the same example but with different approach or different solution of the differential equation. Thank you for watching.